to have Mark Girolami speak this afternoon. Mark is he's a computational statistician, and he holds the Sir Kirby Laing Professorship of Civil Engineering at Cambridge University, where he also holds the Royal Academy of Engineering Research Chair in Data Centric Engineering. Prior to that, Mark has been at the Department of Mathematics at Imperial College. I suppose, really in relevance to a lot of what we want to do out here, Mark was actually one of the originally founders of the Alan Turing Institute, which is the UK's National Institute for Data Science and Artificial Intelligence. He was appointed as the Strategic Program Director at the Turing, where he established Data-Centric Engineering. And Mark now actually is the editor of a journal called Data Centric Engineering. So it is with great pleasure that I welcome Mark to speak to us this afternoon. He'll speak for 30 minutes and then have 30 minutes for questions. Thank you, Mark.
Great. Well, thanks, Sally, and thanks everybody for coming. It's a pity that I can't actually be there, because I always enjoy my trips to visit my friends and colleagues in Sydney. So I'm sitting here just outside my garage in Cambridge. But what I'm going to do today is just really give an overview and of this whole notion of data-centric engineering. And so it's going to be around about 30,000 feet. And if any of you would like a more detailed technical talk, then I'll be more than happy to come back and do that. But I think today this is really just to get some ideas across. So let's just have a look. So what is data-centric engineering? I mean, it would be a very fair statement to say that, look, data has always been the core component within all of the engineering sciences and their practice across pretty much every sector. And, we can look at some of these luminaries here who I would say were data-centric in the way that they actually conducted their own engineering, from Lord Kelvin and the many innovations that he came up with. One of the really lovely examples is his tide predicting machines. His tide predicting machines basically used Fourier analysis and mechanically developed the way in which you could compute the Fourier coefficients to break down the data that was measured from the high and low ebb and flows of the tides, and allowed him to predict machines. So very much not just data driven, but data centric. And then I could go on. Gosset and his development of process control within the brewing industry, Rudolf Kalman, of course, and the whole notion of assimilating data into models of dynamic systems, and the celebrated Kalman filter and all of its variants, and Box, again with quality control within the process industries, and then Shannon, who really formalized the whole notion of information theory, who incidentally, I should say, was probably who kind of topped off much of the fundamental theory that Lord Kelvin started in the commercialization of telegraphy. So the question is, what is new, and do we really need to be talking about engineering as data-centric? Well, I would argue that it does. And it does for a few reasons. So first of all, the sorts of data that Kelvin, Gosset, Kalman, Box, Shannon were dealing with and had to hand was not at the same level of richness as we as scientists have today. We have data at multiple scales, both in time and spatially. And the way in which we can make measurements and the instrumentation that we have available to generate and produce this data with sensor networks that go from the microscopic right through to the global, is producing data at rates, at granularities, and volumes that we really have never experienced before, and that continues almost on an annual basis. And furthermore, the infrastructure that we have in terms of computing, in terms of storing data, assimilating data, retrieving data and processing data, is at global scales that it has really democratized the analysis and use of data in such a ways that, as I said, Kelvin right through to Shannon would never really have experienced. And what this is motivating and driving are whole new areas of theory, both in the basic engineering sciences, but in the underpinning mathematics, statistical science surrounding those. And furthermore, these are giving rise to new technologies, and these technologies are opening up and bringing to life whole new markets. And of course, these new markets require whole new business models that are challenging the way that engineers currently do their business, and are providing great opportunities for new business. And of course, this means that education and skills has to move along with it. So my argument is that engineering has always been data-centric, but the level of prominence of data has now risen to such an extent that we do need to think about new theory to exploit this and look at the sort of technologies that can be developed and will emerge from this. So given that opening argument, then the question is, what was the Alan Turing Institute doing in data engineering? Well, the whole idea was that we would bring together academic institutions from across the UK, along with industrial partners from a number of different engineering sectors. And we looked at moving to different engineering sectors so that we could see common themes and common trends and common technologies and theories that would span those. We could leverage what was being done. And we wanted to address emerging challenges that could potentially be addressed by data-centric engineering. So the whole program at the Alan Turing Institute was established in 2015 by the Lloyd's Register Foundation, and they provided an initial grant of 10 million to get the whole enterprise going. Now, in 2021, what can we look back on? Well, I think the first thing to note is that from that 10 million, most of us as academics are good at going out and getting funding and then spending it down and then going back out with our begging bowls looking for additional funding. Now, the strategy that I put in place was that we would grow this. If data-centric engineering was really going to be an enduring thing of importance, then it was incumbent on us to develop not just an infrastructure locally within the UK, but a community globally. And so at the moment, the program at the Alan Turing Institute is running with an operating budget of 70 million. So we've really grown the program. Excuse me, one of my cats has just decided to join us. And some of the things, a new journal, a new academic journal was established by Cambridge University Press to really promote the whole area of data-centric engineering. The program has gone global, and you'll see that just shortly. And furthermore, in terms of advising the UK government on investments for research and technological research, then the programme has really been foremost in advising. UKRI is similar to the Australian National Research Council, if you will. And we've also been involved in a number of quite significant and quite strategically important projects, which I'll just very briefly touch on. I think the key thing is that the difference between 2015 and 2021 is that if you look across internationally, you will now start to see faculty positions in universities opening up that are looking for data-centric engineering. You'll see centres of doctoral training opening up in data-centric engineering. There are master's programmes opening up in data-centric engineering. And you'll even see companies starting to try to invest in the training and the recruitment of what they are calling data-centric engineers. So there has been tremendous growth and tremendous spread of influence over the last 5-6 years. And here's some of the reach. In North America, the great Odin Institute at the University of Texas, which is the major institute of computational engineering and science. In the Scandic, in the countries such as Finland and Norway, we have major collaborations. And then, of course, in Australia, both on the West Coast, UWA, and in Sydney, we have some thriving and developing collaborations. So DCE is certainly global. Some of the numbers, there are, the top line figure is about 260 plus researchers engaged in the programme across the UK. And well, you can read those numbers there. I won't go into the details. The way that we structured it was that the big challenges that we're really facing are threefold. The first one is that our critical infrastructure is now going to change, and we're seeing this more and more right across the world. And so one of the grand challenges that we instigated was one that would be looking at ways in which we would make our critical infrastructure more resilient and more robust to changes and to shocks. And then the other one, of course, was that if we want to make our infrastructure more robust, we need to be able to monitor the complex engineering systems that infrastructure creates, and you know, how do we monitor it? How do we instrument it? How do we get the right data at the right times? And then the final grand challenge was the use of data, historical data, in the engineering design process. So we had 3 senior academics leading these grand challenges. The other strategic areas were mathematical foundations, education, and energy. And they have all been this program. Strategic, a number of what are called group leaders, and group leaders do exactly what it says in the tin. They lead a group. And each of them was seconded 100% from their home institutions to the Alan Turing Institute. And they were given some seed funding and were asked to make it grow, get more funding, develop more partnerships, recruit more people, and grow the area that you're working on. And you can see some of the areas that we've focused on. In terms of engineering, we've been looking at marine and maritime engineering, environmental engineering, chemical process engineering, infrastructural or structural engineering, technical, and on it goes, aeronautic engineering, and everything around that. And this has really been very successful. The research portfolio, I'm only going to touch on a few of these. One of the really exciting ones that we've led on was a project that came out of Amsterdam, where a number of individuals thought, wouldn't it be a cool idea to 3D print a stainless steel pedestrian bridge and have it span one of the canals in Amsterdam? Now, that was agreed by the Amsterdam City Fathers. They thought this would be a great statement of civic ingenuity and pride. And then someone said, hey, does anyone know what the properties of 3D printed stainless steel are? And structurally, what sort of loads, what sort of levels of safe loading will a structure like this be able to handle? And so I pulled together a team from the Data Centric Engineering program that consisted of structural engineers, materials scientists, applied mathematicians, such as stochastic geometers, would you believe, because the properties, underlying properties of the steel is highly stochastic because of the nature of the way it's produced, and also the fact that there's very little known about it really gives rise to many questions about what its long-term performance will be. And so we put quite a large number of sensors on the bridge. And now that it has been opened and pedestrians are walking over it, it is being used as a living laboratory to look longitudinally at how this will perform. So this is the first in the world, and we're very excited to have been part of this journey. Another very exciting piece of work that we instigated was the use of disused underground rail lines and rail tunnels under London for agriculture, and in particular hydroponic farming. And we, in essence, fitted the whole farm out with a number of sensors. We also built some computational, so mathematical and statistical models, and coupled the sensor networks to the models to deliver what is popularly known today as a digital twin. But it really allowed the prediction and the control of the environment to increase yields within the farm. And this has been a great success, and that work is now ongoing. Some work on dynamic control of power generation and power distribution. One other partnership and one other project that has just kicked off recently, we've received 30 million from the research councils and from the National Air Traffic Service in the UK, is to look at how can the process of air traffic control accommodate the increasing levels of demand for flight. Now, that was in 2018. Things have changed somewhat over the last 2 years, but nevertheless, the need to improve the means in which air traffic is actually controlled leads to very much a data-centric view, using all of this information, all of this data that is available to the air traffic service to improve upon capacity and, of course, safety. And so that's something that we've been working on with them since 2018, and we're just kicking off this quite substantial prosperity partnership project with them just now. I mentioned mathematical foundations, and I think it's absolutely important that we continue to develop novel mathematics, novel statistical methods, because it is really going to underpin most of what is going to emerge from this data-centric perspective. And we have quite a large number of mathematicians who are working with some of the engineering scientists. It was really nice with the 3D printed bridge, as I said, to see stochastic geometers who thought they never had any friends in the world at all, to actually realize that some of their work was going to be incredibly important in characterizing the structural and material properties of 3D printed stainless steel. We have pretty much been in the vanguard of developing this whole notion of digital twins. Digital twin takes what we understand as classical mathematical modeling control and coupling it with the fact that the physical reality of the physical process or system or artifact can now be instrumented and measured again at scales, at rates and at levels that really we were unable to do 50 years ago. And so we have whole research programs on the use, the development of digital twins for multi-phase flows in the process industries, digital twins for infrastructure and construction. I'll give you another example just shortly. We're working and have been working with Rolls-Royce in the aerospace sector, and of course developing the theoretical foundations of engineering digital twins. What if you get two digital, if you get two digital twins of say a couple of bridges, and you want to couple them together, what's the emergent properties? Are we going to increase the predictive capability? Are we going to decrease the variability, or what? I just don't know. And so this theoretical work really has to advance lockstep with the more applied work, which we're pushing ahead with. I mentioned to you the farms. One example I think which is really quite significant is that we were working with the Greater London Authority, who were tackling the major challenge of air pollution in London, a very real environmental problem and a very real hot political potato for the authority. And I set up a team led by who was then the deputy director of the programme, looking at ways in which the quality of air across London could be better measured. So sticking to the dictum that Lord Kelvin made with it, is that if you want to improve something, you need to be able to measure it. And so we established this programme looking at ways in which air quality could be better measured than the quality of data being made available to environmental scientists could be improved. What happened was that Okay, so when we were working on this air pollution, I don't need to give you the motivation for it, but we developed. This is the only techie slide here. We looked at stochastic function approximation and developed what are called deep Gaussian processes. But when the COVID-19 pandemic in March 2020 really took control, both Transport for London and Greater London Authority came to us and asked, we need ways in which we can assess how people and how London and boroughs of London are being compliant to the lockdown. And then subsequently, what is the behaviours of individuals as we start to emerge from that lockdown. So we turned all of this infrastructure into looking at ways in which we could measure and report how busy London was going to be, and do that in real time. So at borough levels, at city levels, and at local levels. And we were providing information to Greater London Authority, to Transport for London, who were then feeding that to Public Health England and assisting the health planners, epidemiologists, and policymakers. And this was a vast undertaking for us, primarily because we were taking data feeds from all of the traffic cameras across London and then using them to come up with indicators of things such as, what is the density of certain types of traffic, whether it's pedestrian traffic, bicycle traffic, car traffic, and so on, and also assessing levels of social distancing and so on. And as I said, that was then fed as information on a daily basis. And we got this very nice letter from the Director's Office at Transport for London, which basically said that the information, the intelligence that was provided to them gave them the information required to implement over 700 interventions, such as widening pavements, moving bus stops, and so on, to support and enable social distancing. So, this was a real triumph, where we were taking things that were being published 12 months before and actually deploying them and using them in the management of the pandemic. In the last couple of minutes, let me just give you one final example. And this is work that was started by my predecessor at Cambridge, Lord Robert Mayer, who's a very well-known geotechnical engineer. And Network Rail, which is the rail operator for all of the UK, we're building a number of new rail bridges in Staffordshire. And when those bridges were being built, a number of fibre Bragg optical sensor networks were embedded within the concrete within the bridges, so that in essence these bridges were able to gather data on the actual structural, in this case, both the strains that were experienced under usage. And that was great. And the problem was that it wasn't clear what was to be done with it. And what we have since done is use the finite element models, but again, because we wanted to take a data-centric approach, the question was, well, finite element methods have really been developed as function approximators in the absence of data. But how can we incorporate data into the finite element method actually take account of the fact that the models that the finite element method is realizing may actually be misspecified. And could we use this data from the physical structures to update and to correct, if you will, our misspecified models? And I believe one of my colleagues from the University of Western Australia has come out to Sydney and spoken about the statistical finite element method at a more technical level. And this is just a little diagram showing that the UK's very first remotely monitored structural asset on all of its rail network is being enabled by the work that my predecessor at Cambridge did, along with the work that my team at Turing have been doing in terms of taking a data-centric perspective to the monitoring and management of structures. So close with a couple of plugs. The first one being the Data Centric Engineering Journal. I would be delighted to see some papers being submitted from Australia. Already we've had papers published from the University of Western Australia. It'd be great to see some from New South Wales. And finally, there's going to be an international Data-Centric Engineering Summit in September 22nd and 23rd. And it would be really great if you would be able to participate and join us during both of those days. So that's me. I think I've managed to stick roughly to 30 minutes. So I'll stop here and we'll now have some sort of discussion.